Tonight, we are going to follow cold to its end. Not the cold of winter, not the cold of a freezer or a high-altitude mountain, or even Antarctica at its worst. We are going to follow cold through the solar system, through interstellar space, through the darkest voids in the universe, and then all the way down to a limit that physics says nothing can ever reach. And then we are going to understand why that limit matters. Why the coldest truth about the universe is not really about temperature at all, but about something deeper. About what matter is when almost all its energy is gone. About what the universe is becoming. And about why cold, more than heat, more than violence, more than any other force in the cosmos, may be the most patient and total thing in existence. The horrifying part is not that space is cold. You already knew that. The horrifying part is what cold actually means when you follow it all the way down. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. The coldest temperature ever recorded on Earth's surface was measured at the Soviet Vostok research station in Antarctica on July 21, 1983. The reading was minus 89.2 degrees Celsius, minus 128.6 degrees Fahrenheit, cold enough that unprotected skin would freeze in seconds. Cold enough that the air itself begins to behave differently, carrying less moisture, conducting less heat, moving differently than it does in the temperate zones. That temperature, minus 89.2 degrees Celsius, is the coldest naturally occurring temperature on the surface of any world that humans have ever walked on. It is a number that feels extreme, remote, far beyond anything most people will ever experience. It is also almost nothing compared to what comes next. The experience of cold at Vostok is not just a number on a thermometer. It is a total assault on everything the body depends on. Exposed metal cannot be touched with bare hands. Fuel behaves differently than it does anywhere else. Machinery fails in ways it would not fail at any temperate location on Earth. The Soviet researchers who staffed Vostok during winter did so in isolation that was not just geographic, but thermal. The cold made the station a sealed world, where the boundary between inside and outside was the difference between survival and death measured in seconds. When the body cools below its operating range, the effects are progressive. First, the periphery cools, as the body restricts blood flow to the extremities to protect the core. The hands and feet lose sensation, become clumsy, stop working. The body is prioritizing the organs over the limbs, a biological hierarchy that reveals how tightly temperature and life are linked. As the core temperature drops further, cognitive function degrades. The chemistry of thought, which requires enzymes operating at specific temperatures, begins to slow. Judgment fails. Speech slurs. Consciousness dims. The body's chemistry, which runs on a narrow operating range of about 36 to 37 degrees Celsius, cannot function at lower temperatures. Below about 28 degrees Celsius in the core, the heart can develop fatal arrhythmias. Below 24 degrees, survival without intervention is uncommon. The coldest core temperature survived in a documented hypothermia case was around 13.7 degrees Celsius in a patient who fell into cold water and was resuscitated in a hospital. That temperature is roughly 24 degrees below normal body temperature. The chemistry of the brain had slowed to near nothing. The chemistry of the heart had nearly stopped. Life had been preserved, temporarily, by the same process that makes deep cold dangerous, the slowing of every reaction. cold does not add something harmful, it takes something away. At Vostok, what it takes away is the warmth that allows chemistry to work. And chemistry is everything. Movement, thought, heartbeat, digestion, all of it requires thermal energy to proceed. There is something specific about the phenomenology of extreme cold that is worth describing before we leave the human scale. In very cold air, the sound behaves differently. At -89 degrees Celsius, the speed of sound drops below what it is at room temperature. Sound travels faster in warmer air. In the cold of Antarctica, sounds carry differently, seem more distant, have a different quality that people who work there describe as part of the eerie character of the continent in winter. Moisture in the air at those temperatures is almost absent. The extreme cold freezes water vapor out of the atmosphere. The air is not just cold but intensely dry. Breathing it without protection risks damaging the airways not just from cold but from dryness. The mucous membranes of the nose and throat, exposed to cold, dry air, quickly lose the moisture they need to function as filters and warmers of incoming air. In winter at Vostok, the sun does not rise at all for several months. The darkness and the cold combine into a total environment unlike anywhere else on Earth's surface. Those who work there in winter are in as profound a kind of sensory and thermal isolation as any humans have experienced on Earth's surface. The nearest warm settlement is hundreds of kilometers away across ice. This is the coldest any human has ever stood, the coldest surface temperature on the planet we evolved on. But even Vostok is not the only way cold defines a human limit. When the body cools below its operating range, the effects are progressive. First, the periphery cools, as the body restricts blood flow to the extremities to protect the core. The hands and feet lose sensation, become clumsy, stop working. The body is prioritizing the organs over the limbs, a biological hierarchy that reveals how tightly temperature and life are linked. As the core temperature drops further, cognitive function degrades. The chemistry of thought, which requires enzymes operating at specific temperatures, begins to slow. Judgment fails. Speech slurs. Consciousness dims. The body's chemistry, which runs on a narrow operating range of about 36 to 37 degrees Celsius, cannot function at lower temperatures. Below about 28 degrees Celsius in the core, the heart can develop fatal arrhythmias. Below 24 degrees, survival without intervention is uncommon. The coldest core temperatures survived after hypothermia are extraordinary outliers, cases where people fell into cold water and were rapidly rewarmed in hospital settings before the cellular damage could become irreversible. In some documented cases, children who fell into frozen water and were submerged for extended periods have been resuscitated with good neurological outcomes, likely because the cold slowed metabolism enough to delay brain death. Cold can, in this narrow and dangerous context, temporarily preserve life by slowing it. But in space, at 2.725 Kelvin or colder, there is no such temporary preservation. There is only the extraction of thermal energy until the chemistry of life has stopped entirely. That temperature, minus 89.2 degrees Celsius, is 184 Kelvin above absolute zero. It is warm compared to what is coming. Mars, at its poles in winter, reaches temperatures around minus 125 degrees Celsius. Colder than Antarctica's record. The transition from Antarctica to Mars is a useful step in understanding cold because it keeps the sense of comparison grounded in things humans have measured and even visited. The Mars record was measured by spacecraft, not by human beings standing in the cold. but the number is directly comparable to Antarctica's, minus 89.2 versus minus 125 degrees Celsius. Mars is colder by 36 degrees. Not a dramatic difference by cosmic standards, but enough to kill anyone not wearing a spacesuit within minutes. What Mars has that Antarctica does not is the absence of liquid water anywhere at its surface at any season. The temperature swings and the low atmospheric pressure combine to keep water in solid or vapor form. The polar caps contain both water ice and carbon dioxide ice. The surface at its coldest is cold enough that carbon dioxide precipitates from the thin air and falls as dry ice snow. Mars is close to the Sun, relatively speaking. It receives meaningful solar energy. It has a thin atmosphere that, even at its most diluted, carries some heat around the planet. These two facts together set a floor on Mars's temperature that the outer planets do not have. Even Mars's polar temperatures represent something human bodies could not survive for a second without protection. But they also represent something the Martian chemistry handles in a specific way. Carbon dioxide, which makes up most of Mars's thin atmosphere, freezes at minus 78.5 degrees Celsius. In Martian winters, carbon dioxide actually snows out of the atmosphere and accumulates at the poles. The polar caps of Mars are not just water ice, they are frozen air. Mercury, the closest planet to the Sun, is a study in contrasts. Its sunlit surface reaches 430 degrees Celsius, hot enough to melt lead. Its night side, with no atmosphere to hold heat, plunges to minus 180 degrees Celsius. Mercury's slow rotation means some craters near the poles never receive direct sunlight, and in those permanently shadowed regions water ice has been detected. A planet close enough to its star to melt lead also has craters cold enough to preserve ancient ice. Venus, despite being farther from the Sun than Mercury, is hotter. Its thick carbon dioxide atmosphere creates a runaway greenhouse effect that maintains surface temperatures around 465 degrees Celsius. Venus is a reminder that temperature on a planet's surface is not determined solely by distance from the Sun. The atmosphere is everything. Earth's surface temperatures range roughly from minus 89 degrees Celsius at the coldest to around 58 degrees Celsius at the hottest, a range of about 147 degrees that life has colonized almost completely. Moving outward, the temperatures fall. Jupiter's visible cloud tops hover around minus 145 degrees Celsius. Saturn's around minus 178. Uranus, despite being closer to the Sun than Neptune, has cloud top temperatures around minus 224 degrees Celsius, colder than Neptune. The reason is that Uranus appears to have lost its internal heat, while Neptune still generates more heat than it receives from the Sun. Two planets of similar size and similar distance from the Sun, one cooling naturally, one retaining heat. Separated by a property we still do not fully understand. At the outer edge of the classical solar system, Pluto averages roughly minus 233 degrees Celsius at its surface. Pluto is warmed slightly by the Sun. At its distance of roughly 40 astronomical units, the sunlight is about 1,600 times weaker than at Earth, but it is there. Neptune's moon Triton has a surface temperature of roughly minus 235 degrees Celsius, colder still. And Eris, the most massive known dwarf planet, sitting at an average distance of about 68 astronomical units from the Sun, likely has surface temperatures approaching minus 240 degrees Celsius. The entire range of the solar system, from Vostok's coldest at 184 Kelvin to Eris at perhaps 30 Kelvin, is still warm compared to what comes after. The Sun, even at its most diluted and distant, imposes a minimum temperature on the objects that orbit it. Mercury illustrates one dimension of this. Despite being the closest planet to the Sun, Mercury's night side falls to minus 180 degrees Celsius because it has no atmosphere to hold heat. The entire thermal history of Mercury's surface is written in its relationship to the Sun, facing the Sun. It is one of the hottest surfaces in the solar system. Turned away, it approaches the temperatures of the outer planets. The Sun giveth and the Sun taketh away, and Mercury has no atmosphere to moderate the extremes. The anomaly of Uranus versus Neptune is one of the more puzzling comparisons in planetary science. Neptune, farther from the Sun than Uranus, is warmer at its cloud tops. The difference appears to be internal heat. Jupiter, Saturn and Neptune all radiate significantly more heat than they receive from the Sun, the residual heat of their formation still leaking outward through their interiors. Uranus does not. It radiates approximately as much heat as it receives. Why Uranus lost or never had significant internal heat is still an open question. Two planets of similar size and composition, one cooling normally, one apparently already cold inside in a way the others are not. Beyond the heliopause, where the Sun's influence gives way to the interstellar medium, the solar minimum disappears. The temperature of an object there is set entirely by the cosmic microwave background, by whatever starlight reaches it from other stars, and by any residual heat from its own formation or composition. And then, when you leave the solar system entirely, something changes. And then when you leave the solar system entirely, something changes. The surfaces of various solar system bodies tell the story of temperature gradients extending outward from the Sun, and placing them in order from warm to cold reveals the full range of temperatures that planetary science has measured directly. Mercury, the closest planet to the Sun, reaches temperatures at its sunlit surface of up to 430 degrees Celsius, hot enough to melt lead. But Mercury rotates slowly and has no atmosphere to distribute heat. On its night side, temperatures plummet to minus 180 degrees Celsius. No planet in the solar system has a wider swing between day and night temperatures. The same world orbiting the same star spans a thermal range that covers more than 600 degrees from face to face. Venus, despite being farther from the Sun than Mercury, is hotter on average. Its thick carbon dioxide atmosphere traps heat so effectively that surface temperatures average around 465 degrees Celsius, hot enough to melt some metals and to destroy any spacecraft that has tried to land there within hours. The extreme greenhouse effect of Venus is a reminder that temperature on a planet's surface is not determined solely by distance from the Sun. Earth's surface temperatures range roughly from minus 89 degrees Celsius at the coldest to around 58 degrees Celsius at the hottest, a range of about 147 degrees that life has colonized almost completely. Mars ranges from around minus 125 degrees Celsius at the poles in winter to about 20 degrees Celsius at the equator on a summer afternoon. A habitable range by Earth standards at its warmest, but a deadly cold at its coldest, with no liquid water possible at the surface under current conditions. Jupiter's cloud tops, where temperature and pressure create conditions loosely analogous to a surface, hover around minus 145 degrees Celsius. The interior is much hotter, as Jupiter radiates more heat than it receives from the Sun, but the visible atmosphere is cold by any human standard. Saturn's cloud tops are around minus 178 degrees Celsius. Uranus reaches minus 224 degrees Celsius in its coldest layers, colder than Neptune's cloud tops despite being closer to the Sun, likely because Uranus appears to have lost its internal heat entirely, while Neptune has not. And then Triton and Pluto and Eris, at the outer edges of the solar system, approaching -230 to -240 degrees Celsius. Cold enough that nitrogen and carbon monoxide are frozen solids on their surfaces. Cold enough that the difference between those worlds and the interstellar medium is only a handful of Kelvin. These temperatures, measured directly by spacecraft or inferred from spectroscopy, represent the full range of what the solar system provides. Below this range, you are beyond the solar system, in the domain of the cosmic microwave background. In the space between stars, there is no nearby star to warm you, no planet to reflect heat, no atmosphere, no magnetic field from a friendly world. But empty space is not simply cold in the way a room with no heating is cold. The concept requires unpacking. Temperature is a measure of the average kinetic energy of particles, the average speed at which atoms or molecules are moving. More motion means higher temperature. Less motion means lower temperature. In a perfect vacuum with no particles, there are no particles to have kinetic energy. The concept of temperature simply does not apply in the usual sense. A perfect vacuum has no temperature because temperature is a property of matter, not of empty space. What does fill space, however, is radiation. The electromagnetic field of deep space is not empty. It is permeated by photons traveling in all directions, light from distant stars and galaxies, various forms of radio and microwave radiation, and above all else the cosmic microwave background. This photon field has a characteristic temperature. It behaves the same way a black body radiator at a specific temperature would behave, and that temperature is approximately 2.725 Kelvin. So when scientists say that deep space has a temperature of about 2.725 Kelvin, they are technically describing the temperature of the radiation field, not the temperature of the vacuum itself. If you placed a thermometer in deep interstellar space, far from any star, it would eventually equilibrate with the surrounding radiation field and read approximately 2.725 Kelvin. The thermometer has particles. Those particles absorb and emit photons. When they reach equilibrium with the photon field, you have a temperature. But the vacuum between the photons has no temperature. This distinction is not just technical. It points to something important about what cold in space actually is. Cold in space is not the absence of something. It is the specific state of a radiation field that fills all of space. The 2.725 Kelvin background is not a local condition. It is everywhere. In your room right now, CMB photons are passing through you at a rate of hundreds per second. They carry so little energy that they interact with nearly nothing in ordinary matter. But they are there. The 2.725 Kelvin glow of the early universe is not confined to deep space. It fills all space, including yours. What the deep interstellar environment adds is the removal of everything else. No stellar radiation, no planetary reflection, no atmospheric scattering, only the background photon field, arriving uniformly from every direction. A whisper of ancient light that holds the universe just barely above its own thermal floor. This distinction matters because it points to something deeper about what cold in space actually is. Cold in space is not primarily the absence of matter. It is the state of the radiation field that permeates all of space. The 2.725 Kelvin background is not a local condition. It is everywhere. In your room right now, CMB photons are passing through you at a rate of hundreds per second. They carry so little energy that they interact with nearly nothing in ordinary matter. But they are there. The 2.725 Kelvin glow of the early universe is not confined to the spaces between galaxies. It fills all space, including the air around you, including your body, including the most insulated human-built room on Earth. What you feel as room temperature, roughly 293 Kelvin, is the superposition of many energy sources: sunlight absorbed by the ground and radiated as infrared, heat from human metabolism, heat from the warm air, the thermal radiation of the walls. All of this sits on top of the 2.725 Kelvin background that fills the universe. Strip all of that away, take yourself to a location far from any star, and what remains is the background. Not nothing, not emptiness. The residual glow of an event 13.8 billion years ago, spread across all of space in all directions at once, holding the universe barely above its own floor. That is what cold in space is. Not the absence of the universe, the minimum that the universe provides. The cosmic microwave background is not just the ambient temperature of space. It is something more specific and more significant. The residual heat from the Big Bang, stretched by the expansion of the universe over 13.8 billion years from the intense glow of the early universe into long wavelength microwave radiation. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before that moment, the universe was so hot and dense that photons could not travel freely. They were constantly scattering off charged particles in a fog of plasma. The universe was opaque. Every photon that tried to travel more than a tiny distance would immediately interact with a charged particle and change direction. When atoms formed, the fog cleared. Light was suddenly free to travel. And the light that was released at that moment has been travelling through space ever since, stretched by the expansion of the universe from the orange glow wavelengths of 3,000 Kelvin into the faint microwave radiation of 2.725 Kelvin that fills all of space today. This is the light you would be immersed in if you floated in deep interstellar space, with no nearby star and no planetary body close. Not darkness, not warmth, just this ancient, stretched, cooling glow arriving from every direction simultaneously, the afterimage of an event that happened 13.8 billion years ago. The universe has cooled by a factor of roughly 1,000 since last scattering. What was 3,000 Kelvin orange hot plasma is now a 2.725 Kelvin microwave whisper. The same light. The same photons, more or less, stretched by the expansion of the universe until their energy dropped by a factor of 1,000. And it is still cooling, not quickly. The expansion continues. The photons continue to be stretched. The temperature of the cosmic microwave background will be lower in 1 trillion years than it is today, lower still in 10 trillion. The ancient glow is fading, slowly and continuously, as the universe expands away from its own beginning, 2.5 degrees above absolute zero, a whisper of ancient light keeping the universe fractionally above its own floor. The CMB is not perfectly uniform. The COBE satellite in 1992 first detected the tiny temperature variations in the CMB that had been predicted. These variations, on the order of 1 part in 100,000, are the imprint of density variations in the early universe from which all structure grew under the influence of gravity. Regions that were very slightly denser than average in the early universe were very slightly warmer. Their light arrived at the moment of last scattering very slightly more energetic. over 13.8 billion years, that very slight excess energy has become a very slight excess temperature in the CMB. And those slightly denser regions are the seeds from which galaxies and galaxy clusters grew under the pull of gravity. The CMB maps produced by COBE map and the Planck satellite encode the entire subsequent history of cosmic structure in their temperature patterns. They reveal the geometry of the universe, the ratio of ordinary matter to dark energy, the rate of expansion, and the specific spectral shape of the primordial density variations that seeded all the structure we observe. All of this information is preserved in photons that have been travelling for 13.8 billion years, stretched from visible light into microwaves, carrying a temperature of 2.725 Kelvin, with tiny variations that speak volumes about the universe's origins and composition. The coldest glow in the universe is also its most ancient letter. Across the universe, the CMB temperature varies by only about 1 part in 100,000 from point to point. This extreme uniformity was itself a puzzle. If the early universe had different regions at different temperatures, how could regions separated by billions of light years, which could never have been in contact with each other given the speed of light, end up at the same temperature to such extraordinary precision? This problem, called the horizon problem, was one of the motivating puzzles for the theory of cosmic inflation. Inflation proposes that the very early universe underwent a period of extraordinarily rapid expansion, much faster than the speed of light, stretching a tiny region of space into the observable universe we see today. In this scenario, the entire observable universe originated from a tiny region that was small enough to be in thermal equilibrium. Inflation expanded that uniform region until it became the uniform CMB we observe. The uniformity of the CMB, its near-perfect 725 Kelvin across the entire sky, is therefore evidence for one of the most dramatic proposals in modern cosmology, that the universe we observe is a tiny expanded fraction of a region that was once in perfect thermal contact, stretched in an instant to cosmic scale. The tiny temperature variations in the CMB, the 1 part in 100,000 deviations, are the seed of all structure. The near-perfect uniformity is the evidence of a cosmological event that happened before the universe was a fraction of a second old. The coldest glow in the universe carries the oldest news in the universe, and it is visible to the right instruments from anywhere in the cosmos simultaneously. But there is a place in the universe colder than this background. In the direction of the southern constellation Centaurus, roughly 5,000 light-years from Earth, there is a structure called the Boomerang Nebula. It is what happens when a dying star expels its outer layers into space, but expels them faster than almost any other object of its kind has been observed to do. The star at the centre of the Boomerang Nebula is losing mass at an extraordinary rate, and it is expelling that mass as a high-speed outflow, moving at approximately 164 kilometers per second. That velocity matters because when gas expands rapidly into a vacuum, it cools through a process called adiabatic cooling. The kinetic energy of the expansion is extracted from the thermal energy of the gas. The gas cools as it spreads. On Earth, this is the principle behind refrigerators and air conditioners. Expanding gas cools. A bicycle tyre valve with air rushing out is noticeably cool to the touch. The expansion extracts thermal energy from the gas. Here, the gas is expanding at 164 kilometers per second into the surrounding space, and the cooling is so rapid and so complete that the outflow drops below the temperature of the cosmic microwave background. Below it. This is not just any cold spot. This is a region of the universe colder than the background radiation that fills all of space. It has been measured at approximately 1 Kelvin, 1 degree above absolute zero. The cosmic microwave background, which fills all of space at 2.725 Kelvin, is actually warming the Boomerang Nebula from the outside. The background radiation flows in from every direction and heats the cold outflow slightly. Without the CMB, the Boomerang would be colder still. The Boomerang Nebula is a temporary phenomenon. The expansion cannot continue indefinitely. As the gas slows and disperses, as the expansion rate drops, the cooling effect diminishes. The gas will eventually reach equilibrium with the CMB at 2.725 Kelvin. The Boomerang Nebula's record cold is a phase, not a permanent state. It is, as of the most recent measurements, the coldest known natural place in the observable universe. Not the coldest thing humans have created in a laboratory, the coldest thing nature has produced that we have found. The Boomerang Nebula was discovered in 1980 and named for its shape in early telescope images. Its extraordinary cold was identified later through radio telescope observations that could detect the microwave emission from the cold gas outflow. The measurement that the outflow was colder than the cosmic microwave background was not intuitive. Most cold nebulae are warmed by the surrounding CMB to at least 2.725 Kelvin. Finding something colder required a very specific physical circumstance. Gas expanding fast enough that adiabatic cooling overtook the CMB warming before the gas could equilibrate. The fact that the Boomerang Nebula exists tells us something about what the natural universe can achieve through physical processes. A temperature of 1 Kelvin, far below any planet or moon in the solar system, far below interstellar space, just barely above the quantum floor. But even 1 Kelvin is, by laboratory standards, not very cold. A Bose-Einstein condensate cooled in a laboratory sits billions of times below that. The natural universe's most extreme thermal achievement is easily surpassed by human technology in a table-sized apparatus. 1 Kelvin. 1 degree above the floor, the universe's coldest achievement. Nature's best attempt. And still hundreds of millions of times warmer than what a laboratory can reach. The mechanics of how gas cools when it expands, the process that makes the Boomerang Nebula the coldest known natural place, is worth understanding because it also explains how refrigerators work, how air conditioners work, and how some of the coldest temperatures in laboratories are achieved. When a gas expands into a lower pressure region, the gas molecules push against the expanding boundary. This work of pushing against the boundary uses kinetic energy. The molecules slow down, they become less energetic, and lower kinetic energy means lower temperature. This is called adiabatic expansion, when it happens without heat transfer into or out of the gas. The cooling is driven entirely by the work the gas does as it expands. If you prevent heat from flowing in from outside, all the energy used for the expansion must come from the thermal energy of the gas itself, which cools as a result. On a small scale, this is what happens in a bicycle tire when you let the air out quickly. The air leaving the valve is noticeably cooler than the air in the tire. The expansion cools it. On a large scale, this is what happens in the Boomerang Nebula. A dying star at the center is expelling gas through 2 lobes, creating what astronomers call a bipolar outflow. The gas is moving at about 164 kilometers per second, which is fast enough that the expansion is rapid and the cooling is extreme. In laboratory cooling, similar principles apply, and the progression from room temperature to near absolute zero requires a sequence of different techniques, each working over a different temperature range. At room temperature, the starting point is an ordinary gas in an enclosed chamber. The first step might be simple compression and expansion cooling. Compress the gas, let it cool by contact with the room, then rapidly expand it. The expansion cools it below room temperature. This is the principle behind your home refrigerator and air conditioner. Cryogenic liquids take over from there. Liquid nitrogen at 77 Kelvin can cool objects well below what simple mechanical refrigeration achieves. Liquid helium-4 at 4.2 Kelvin goes much colder. By reducing the pressure above a liquid helium bath, you can cause the helium to boil at a lower temperature, reaching about 1st Kelvin. Superfluid helium bath cooling can reach 0.3 Kelvin. Dilution refrigerators, which use the mixing entropy of helium-3 and helium-4 isotopes in a specific configuration, can reach temperatures in the millikelvin range, thousandths of a degree above absolute zero. These are the machines that cool quantum computers. Laser cooling traps atoms with precisely tuned laser beams and uses the momentum exchange between photons and atoms to slow them down. Each photon absorbed by an atom gives the atom a tiny push opposing its motion. Over millions of such interactions, the atoms slow dramatically. Evaporative cooling removes the most energetic atoms from a trapped group, leaving behind only the slower, colder ones. Just as the fastest molecules at the surface of a hot drink carry the most energy away when the drink evaporates, removing the fastest atoms from a trapped cold gas lowers the temperature of what remains. These last steps take the temperature into the nanokelvin and picokelvin range, where quantum effects dominate and Bose-Einstein condensates can be created. Each step requires more sophisticated equipment. Each step yields less cooling per unit of energy invested. Each step is harder than the previous one. Each step closer to the floor requires more effort to reach. All of them are versions of the same basic physics. To make something cold, you extract its thermal energy by doing work on it, or allowing it to do work on its environment. Cold is not added. Heat is removed. And the work required to remove heat increases without limit as you approach zero. To understand what cold really means at these scales, you need to understand what temperature is. Temperature is a measure of the average kinetic energy of particles, the average speed at which the atoms or molecules in a substance are moving, bouncing, vibrating. More motion means higher temperature. Less motion means lower temperature. This is the entire content of the concept. Temperature is not a property of empty space. It is not a cosmic constant. It is a statistical description of how fast the particles in a material are moving. In a perfect vacuum with no particles, there are no particles to have kinetic energy. Temperature simply does not apply. In a gas, temperature is the average energy of the random, chaotic motion of the molecules. In a solid, it is the average energy of the vibrations of the atoms around their fixed lattice positions. Heat, which is often confused with temperature, is the transfer of this kinetic energy from one system to another when they are in contact. Hot things have particles moving fast. Cold things have particles moving slowly. When you touch a cold metal surface and it feels cold, what is happening is that the metal atoms, moving slowly because they have less kinetic energy, are drawing kinetic energy from the atoms in your skin. The sensation of cold is the sensation of energy leaving your body. The Celsius scale is built around the freezing and boiling points of water, which are convenient for everyday life but have no fundamental physical significance. The Fahrenheit scale is built around even more arbitrary anchors. The Kelvin scale is built around absolute zero. 0 Kelvin is not a convention. It is the point at which the thermal energy of matter reaches its theoretical minimum. Every Kelvin above 0 represents a fixed amount of thermal energy per particle. Room temperature, roughly 20 degrees Celsius, is about 293 Kelvin. Body temperature, 37 degrees Celsius, is 310 Kelvin. The coldest place on Earth's surface, at minus 89.2 degrees Celsius, is about 184 Kelvin. The Boomerang Nebula at 1 Kelvin has 1 unit of thermal energy above the floor. The gap between Antarctica's coldest recorded temperature and the coldest natural spot in the universe is almost the entire range of the Celsius scale. The Kelvin scale reveals this. The Celsius scale hides it. These numbers, expressed in Kelvin, reveal something the Celsius scale obscures. Even the coldest natural temperature on Earth's surface is 184 Kelvin, which means it has 184 units of thermal energy above absolute zero. The gap between Antarctica and the Boomerang Nebula is most of the Kelvin scale. What remains below the Boomerang, between 1st Kelvin and 0, is territory that only laboratories have entered. In an ordinary gas at room temperature, individual molecules are moving in random directions at speeds that span a wide range. The distribution of speeds follows a well-defined mathematical pattern called the Maxwell-Boltzmann distribution. Some molecules are moving very fast, some slowly, but the average speed is set by the temperature. Higher temperature means higher average speed. Lower temperature means lower average speed. At room temperature, about 293 Kelvin, the average speed of nitrogen molecules in the air around you is roughly 515 meters per second, faster than the speed of sound. At the temperature of the Boomerang Nebula, 1st Kelvin, the equivalent average speed would be a tiny fraction of that. The molecules would barely be moving at all by the standards of everyday experience. But this slowing has a consequence that goes beyond just the speed. In a warm gas, molecules are constantly colliding with each other, exchanging energy, changing directions, interacting. These collisions are the mechanism by which heat is transferred from hot regions to cold regions, and by which chemical reactions proceed. Remove the kinetic energy, and the collisions slow. Remove enough of it, and chemistry stops. This is the connection between cold and biology. Life requires chemistry. Chemistry requires thermal energy. Cold is the removal of the energy that chemistry runs on. The Kelvin scale, because it is anchored to the actual minimum of thermal energy, makes this visible. A temperature of 293 Kelvin is not just a number. It is a measure of how much energy the molecules around you have and how fast they are moving. A temperature of 1 Kelvin tells you that the molecules have almost none of that energy left. Absolute zero is 0 Kelvin. Minus 273.15 degrees Celsius. The temperature at which atoms have the minimum possible thermal energy, the lowest state of kinetic motion that thermodynamics allows. It cannot be reached. The third law of thermodynamics states that it is impossible to reach absolute zero through any finite sequence of processes. Think about what this means practically. If you want to cool something from room temperature to very cold, you use a refrigerator. A refrigerator works by moving heat from the inside to the outside, powered by energy. To cool something further, you need a more powerful refrigerator, more energy, more precision. As you approach absolute zero, each degree of cooling becomes harder. Not linearly harder, exponentially harder. To cool something from 10 Kelvin to 9 Kelvin, requires more effort than to cool it from 100 Kelvin to 90 Kelvin. To cool something from 1 Kelvin to 0.1 Kelvin requires vastly more effort still. Each step towards zero is harder than the last. The mathematics works out such that to reach exactly 0 Kelvin would require an infinite number of steps, each extracting a smaller and smaller amount of heat, and no finite amount of work can accomplish an infinite number of steps. Absolute zero is like a horizon that you can approach but never reach. You can always get closer. You can halve the distance. You can halve it again. But the path requires infinite steps, and infinity is not achievable in a finite universe with finite time and finite energy. This is not a statement about our technological limitations. It is a statement about what the universe allows. No object in the universe has ever been at absolute zero. No object ever can be. The coldest state anything can occupy is always some small but non-zero distance from the true floor. The third law has a practical consequence that is felt in every experiment that tries to reach low temperatures. Every method of cooling becomes less efficient as you approach zero. Laser cooling, which can bring atoms from room temperature to the microkelvin range, stops being able to cool further once the atoms are so slow that the momentum kicks from photon absorption heat them as much as they cool them. Evaporative cooling, which removes the fastest atoms to lower the average energy of those remaining, stops working once so few atoms remain that the cloud is not large enough to function as a well-defined thermal system. Each cooling technique works over a specific range of temperature and then hands off to the next method, which works over a lower range, and so on. A dilution refrigerator reaches millikelvin. Adiabatic demagnetization can reach microkelvin. Laser cooling can reach nanokelvin. Evaporative cooling can reach picokelvin. Each step requires more sophisticated equipment, more isolation from the environment, more precise control, and each step is harder than the previous one. The universe enforces the third law not by some explicit prohibition, but by making each successive cooling step require more work per unit of temperature reduction. The floor is not protected by a wall. It is protected by an ever-steepening slope. The idea that there was a lowest possible temperature was proposed mathematically in the early 1700s by the French physicist Guillaume Amontons. The idea that there was a lowest possible temperature was proposed mathematically in the early 1700s by the French physicist Guillaume Amontons. In 1702, Amontons was studying the relationship between gas pressure and temperature. He noticed that as gas cooled, its pressure decreased in a regular way. By extrapolating this relationship downward, he suggested there must be a point where the gas pressure would reach zero, and that this point would represent the lowest possible temperature. Amontons estimated this lowest temperature at around minus 240 degrees Celsius, within about 33 degrees of the correct value. For someone working with the physics of the early 18th century, with no atomic theory and no quantum mechanics, this was a striking piece of reasoning. Over the following century, scientists refined the concept. Jacques Charles and Gay Lussac developed what became Charles's law. Lord Kelvin, William Thomson, in the mid-19th century formalized the scale that bears his name and established the thermodynamic basis for absolute zero. Kelvin understood not just that there was a minimum temperature, but why. It corresponds to the minimum of thermodynamic entropy, the most ordered state matter can occupy, the point at which there is no remaining thermal randomness to extract. Over the following century, scientists refined the concept. Jacques Charles and later Gay Lussac developed what became known as Charles's law, which describes the relationship between gas volume and temperature precisely enough to allow better extrapolation to zero. The 0 point they identified fell at roughly what we now call absolute zero. It was Lord Kelvin, William Thomson, who in the mid-19th century formalised the scale that bears his name and established the thermodynamic basis for absolute zero. Kelvin understood not just that there was a minimum temperature, but why. The minimum corresponds to the minimum of thermodynamic entropy, the most ordered state matter can occupy, the point at which there is no remaining thermal randomness to extract. The concept was then refined further by the development of statistical mechanics and eventually quantum mechanics, which added the crucial insight that absolute zero does not mean zero energy. It means zero thermal energy, but quantum mechanics ensures that some residual energy, the 0 point energy, can never be removed. What Amintons glimpsed mathematically in 1702 took nearly 3 centuries of physics to fully understand. Here is what makes absolute zero genuinely strange. Even if you could reach it, perfect stillness would not be what you found. Absolute zero is not the point where all motion disappears. It is the point where classical thermal motion reaches its minimum. Quantum mechanics still leaves matter with 0 point energy, a final irreducible motion that cannot be removed. The Heisenberg uncertainty principle states that you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of measurement, it is a feature of reality itself. If an atom were truly at rest at absolute zero, you would know both its position and its momentum simultaneously with perfect precision. Its momentum would be exactly zero. Its position would be wherever it sat. But this would violate the Heisenberg uncertainty principle. The universe does not allow it. Therefore, even at absolute zero, atoms retain a residual vibration. They cannot be completely still. Even in the coldest possible state, there is motion. Small, irreducible, quantum mechanical motion that exists not because the atom is warm, but because the laws of physics forbid perfect stillness. Helium-4 demonstrates this at a macroscopic scale. At normal pressure, helium never freezes, regardless of how cold you make it. The 0 point vibrations of helium atoms are energetic enough, and the forces between helium atoms weak enough that the atoms cannot lock into the fixed positions of a solid crystal. You must apply external pressure to force helium into a solid state. The quantum energy of motion prevents crystallization at any temperature without additional forcing. There is a counterintuitive extension of this in quantum systems with negative temperatures. In certain atomic spin systems, it is possible to prepare a state where higher energy states are more populated than lower energy states. This is the opposite of what happens in ordinary thermal equilibrium. When a system is inverted in this way, it can be assigned a negative temperature in a technical mathematical sense. Not in the sense of being colder than absolute zero, that is physically impossible, but in the sense that the equations of thermodynamics applied to this inverted system yield a negative number. Negative temperatures in this technical sense are hotter than any positive temperature. A system at negative temperature will spontaneously transfer heat to any positive temperature system it contacts, no matter how hot that positive temperature system is. These negative temperature states have been realized experimentally in cold atom systems. What this reveals is that temperature itself is more nuanced than the simple intuition of hot and cold suggests. Temperature is not just a measure of how much thermal energy a system has, it is a measure of how that energy is distributed across the available energy states. Cold is not just low energy, it is energy concentrated in the lowest available states. Cold, pushed all the way to its absolute limit, does not produce stillness. It produces a minimum of motion that cannot be extracted. The floor is not still. It is only as still as the universe allows. The connection between zero-point energy and the structure of matter runs throughout chemistry and materials science. It is not a curiosity of extreme physics. It affects the behavior of every solid and every molecule. The specific heat of solid materials at very low temperatures, the amount of heat required to raise their temperature by a fixed amount, decreases towards zero as temperature approaches absolute zero. This is a prediction of quantum mechanics that classical physics could not explain. Classical physics predicted that the specific heat should remain roughly constant at low temperatures. Experiments in the early 20th century showed it dropping sharply towards zero. This discrepancy between classical prediction and experimental reality was one of the early signs that something fundamentally new was needed to explain the behavior of matter at low temperatures. The resolution came through quantum mechanics, specifically the quantization of vibrational modes in solids proposed by Albert Einstein in 1907 and refined by Peter Debye in 1912. Their models predicted the correct behavior of specific heats at low temperatures, one of the early triumphs of quantum theory applied to solid-state physics. The fact that quantum mechanics was first confirmed in part through the study of cold matter is not a coincidence. Cold removes the thermal noise that allows classical approximations to work reasonably well at high temperatures. At low temperatures, the quantum reality cannot be averaged away. It must be confronted directly. Cold is therefore not just a physical condition. It is an experimental lens, a tool for removing the thermal veil that hides the quantum nature of matter at ordinary temperatures. The floor is not still. It is only as still as the universe allows. The phenomena that emerge as you approach absolute zero are among the strangest in physics. They are not exotic edge cases. They are what matter actually is when you remove enough thermal noise to let its quantum nature become visible. In ordinary matter at room temperature, atoms behave roughly like classical particles. They move in defined paths. They have specific positions and velocities at any given moment. The quantum nature of matter is always present, but the thermal noise of room temperature motion averages it away. The individual quantum behavior of each atom is lost in the crowd. As temperature drops, this thermal noise decreases. The random motion quiets, and as it quiets, quantum effects become visible at larger and larger scales. Superconductivity is one of the first things to emerge. In ordinary conductors, electrons moving through a material encounter resistance. They interact with the atoms of the material, lose energy to those interactions, and this resistance generates heat. This is why copper wires warm when current flows through them. But in certain materials cooled below a critical temperature, usually a few degrees above absolute zero, something changes. Electrons pair up into quantum mechanical pairs called Cooper pairs, and these pairs can move through the material without resistance. Zero resistance, not low resistance. 0A current started in a superconducting loop will continue flowing forever with no energy input, as long as the temperature is maintained. This is not approximately true, it is exactly true. A current that flows without any energy loss is genuinely different in kind from any ordinary current. Superconductivity is one of the clearest manifestations of quantum reality at the human scale. The practical consequence is enormous. The powerful magnets in MRI machines, in particle accelerators, in experimental fusion reactors, all depend on superconductivity. Without the ability to maintain zero resistance currents, the magnetic fields required for these applications would require continuous massive energy input and generate enormous waste heat. An MRI machine illustrates this concretely. A clinical MRI scanner typically produces a magnetic field of 1.5 to 3 Tesla. To produce a field that's strong using ordinary copper wire resistive magnets would require enormous power and would generate so much heat that the cooling system would be a dominant part of the machine's size and cost. With superconducting magnets maintained near absolute zero, the field runs with zero resistance, consuming energy only to maintain the temperature rather than to fight resistive losses. The magnet coils in a clinical MRI machine carry currents of thousands of amperes with zero resistance. Once energized, the current in a well-maintained superconducting magnet continues flowing indefinitely without any additional energy input. This is not an approximation. It has been directly verified by winding a superconducting loop, starting a current in it, and measuring the current months and years later with no measurable decay. The quantum phenomenon of superconductivity, which requires temperatures near absolute zero to manifest, is the reason your doctor can see the soft tissues inside your body without surgery. The cold is not incidental to the technology. It is what makes the technology physically possible. The cold that makes MRI machines possible is typically around 4 Kelvin, maintained with liquid helium. Superfluidity is what happens to liquid helium when it is cooled below approximately 2.17 Kelvin. Below this transition point, helium-4 enters a superfluid phase where it flows with zero viscosity, not low viscosity. 0. Superfluid helium conducts heat extraordinarily efficiently and supports unusual wave-like modes of motion that ordinary liquids cannot produce. It can pass through holes so small that no ordinary liquid could penetrate them. In the laboratory, superfluid helium climbs the walls of its container, driven by the thin film of superfluid coating every surface, and flows over the rim and drips off the bottom of the flask in defiance of gravity's attempts to keep it in place. Helium-3, the rarer isotope, also becomes superfluid at much lower temperatures, around 2.5 millikelvin, through a different mechanism. Helium-3 atoms are fermions, not bosons, and they pair up through a process analogous to the Cooper pairing in superconductors. The helium-3 superfluid was discovered in 1972 and earned the Nobel Prize in Physics in 1996. Bose-Einstein condensation is what happens when an entire collection of atoms is cooled until their quantum wavelengths overlap. At room temperature, each atom has a quantum wavelength much smaller than the distance between atoms. They behave as individual particles. As you cool them, their wavelengths grow. Below a critical temperature, the wavelengths overlap completely, and something qualitatively new happens. The atoms cease to be individual. They merge into a single quantum state, a collective wave function that occupies visible space. In 1995, Carl Wieman and Eric Cornell at the University of Colorado created the first Bose-Einstein condensate of rubidium atoms cooled to 170 nanokelvin, about a 170 billionths of a degree above absolute zero. What they had created was matter in a state that had never existed naturally anywhere in the universe. A cloud of thousands of atoms behaving as a single quantum entity. What this means concretely is worth dwelling on. In an ordinary gas, each atom has its own position, its own velocity, its own quantum state. The atoms are distinguishable from each other in principle, even if measuring each one individually is not practical. They are individuals in a crowd. In a Bose-Einstein condensate, this individuality disappears. All the atoms simultaneously occupy the single lowest energy quantum state available. They do not each have their own wave function. They share a single collective wave function that describes all of them simultaneously. The condensate is, in a very precise quantum mechanical sense, not a collection of atoms but a single entity described by a single equation. This collective wave function has visible consequences. In a condensate, laser light passes through differently than through an ordinary gas. The refractive properties change. The condensate can absorb and re-emit light in ways that individual atoms cannot. And these collective optical properties can be used to study the quantum nature of the condensate directly. In 1999, Lene Howe at Harvard University slowed light to 17 meters per second, and later to a complete stop, by passing it through a Bose-Einstein condensate. The light did not cease to exist inside the condensate. It was encoded into the collective quantum state of the atoms and later retrieved. Light stopped, held and released by matter in a quantum state that requires temperature in the billionths of a degree. In an ordinary gas at room temperature, individual atoms are moving in random directions at high speeds. The distribution of speeds follows the Maxwell-Boltzmann distribution. Some molecules move fast, some slowly, but the average is set by the temperature. This means you cannot say exactly where any individual atom is, or precisely how fast it is moving at any moment. Thermal motion produces a kind of fundamental randomness. As temperature drops, this randomness decreases. The atoms move more slowly, the range of speeds narrows. At very low temperatures, the quantum wavelengths of atoms grow large enough to overlap, and the atoms can no longer be treated as individual particles. They merge into a collective quantum state. The Bose-Einstein condensate is not a very cold gas. It is a different phase of matter, a new state that has no classical analogue. The 2001 Nobel Prize in Physics was awarded for its experimental realization. Helium-3, the rarer isotope, also becomes superfluid at much lower temperatures, around 2.5 millikelvin, through a different mechanism. Helium-3 atoms are fermions rather than bosons, meaning they cannot directly occupy the same quantum state in the way helium-4 atoms can. But at sufficiently low temperatures, helium-3 atoms pair up through quantum mechanical interactions into pairs that together behave as bosons, and helium-3 also becomes superfluid through this pairing mechanism. The helium-3 superfluid was discovered in 1972 by Douglas Osheroff, Robert Richardson, and David Lee. The work earned the Nobel Prize in Physics in 1996. The physics of helium-3 superfluidity is closely analogous to the BC's theory of superconductivity, where electrons in a superconductor pair into Cooper pairs that move without resistance. In both cases, pairing at low temperatures creates a new collective quantum state that behaves fundamentally differently from the individual particles that compose it. What links all of these phenomena is the removal of thermal noise. At room temperature, thermal energy overwhelms the delicate quantum correlations that produce superconductivity, superfluidity, and Bose-Einstein condensation. The atoms are moving too fast and randomly for any collective quantum behavior to persist. As temperature drops, the thermal noise decreases. The quantum correlations, which were always present in the underlying physics, become dominant. These phenomena share a common origin. They are what matter actually is when you strip away the thermal noise that ordinary temperatures impose. The quantum reality was always there. Cold makes it visible. How cold have we gotten? The natural coldest temperature in the universe is the Boomerang Nebula at approximately 1st Kelvin. Laboratory experiments have cooled small samples of matter to temperatures measured in nanokelvin, billionths of a degree above absolute zero, and in some cases picokelvin, trillionths of a degree. In 2003, researchers at MIT created a sodium gas Bose-Einstein condensate at 450 picokelvin. That is 0.0045 Kelvin, roughly 2 billion times colder than the Boomerang Nebula. The natural universe's coldest known place is, in laboratory terms, barely even cold. NASA's Cold Atom Laboratory operates on board the International Space Station. On Earth, an ultra-cold gas cloud is pulled downward by gravity, falling out of the trapping region in fractions of a second. In the microgravity of orbit, the cloud can be prepared and held for longer, allowing experiments that are impossible on the ground. Experiments on the Cold Atom Laboratory have pushed into the picokelvin range for extended periods. The International Space Station orbits at an altitude of roughly 400 kilometers above Earth's surface. In the shadow of the Earth, the temperature of any surface on the ISS drops dramatically. Without sunlight, the only source of warmth is the thermal radiation emitted by the Earth below and the faint cosmic microwave background. Temperatures in the shaded parts of the station can fall to around minus 150 degrees Celsius, roughly 120 Kelvin. On the sunlit side, temperatures can rise to over 120 degrees Celsius. The ISS thermal management system handles a swing of 270 degrees Celsius between shadow and sunlight. And inside that same station, the Cold Atom Laboratory creates temperatures billions of times colder than the surrounding interstellar medium. The Large Hadron Collider's superconducting magnets operate at 9 Kelvin inside an accelerator ring 27 kilometers in circumference, located underground near Geneva. The magnets are cooled with superfluid helium, which at 1.9 Kelvin has extraordinary heat-conducting properties that prevent local temperature spikes when particles are absorbed by the magnet structures. The Large Hadron Collider's superconducting magnets operate at 9 Kelvin, colder than the cosmic microwave background, but still warmer than the Boomerang Nebula's roughly 1 Kelvin outflow. The entire cooling system for the LHC, with its 232 main dipole magnets, represents one of the largest refrigeration systems ever built. The total amount of liquid helium involved exceeds what is available in most national stockpiles. The energy required to maintain 9 Kelvin across 27 kilometers of underground magnets is substantial. All of this to produce the magnetic fields needed to bend and focus beams of protons moving at 99.9999991% of the speed of light, so that those protons can collide and recreate, briefly, the conditions of the very early universe when temperatures were billions of degrees and the matter we are made of was not yet assembled into its current forms. The cooling system for the LHC is itself an engineering achievement worth describing. The 1,232 main dipole magnets, each about 14 meters long and weighing roughly 35 tons, must all be maintained at 1.9 Kelvin simultaneously. Any individual magnet that warms above its critical temperature would immediately lose its superconducting state, causing the current to stop suddenly. The sudden stopping of a current that had been carrying thousands of amperes would dissipate an enormous amount of energy in a very short time. This event, called a quench, must be managed carefully to prevent damage to the magnet. The cooling is achieved using approximately 120 tons of liquid helium circulated through the magnet coils, cooled to 9 Kelvin using a system of refrigeration plants located around the ring. The total refrigeration capacity required to maintain this temperature across 27 kilometers of magnets is substantial. Operating the LHC cooling system is a significant industrial operation in its own right, separate from the physics it enables. When the LHC is not running, maintaining it at 9 Kelvin uses roughly a third of its total power consumption. Cold costs energy, cold costs effort, cold costs infrastructure. The universe trends toward cold for free. Humans have to pay to get there. The coldest place in the known universe, for about 27 kilometers in a loop under Switzerland and France, requires an industrial operation to maintain. The coldest place in the known universe, for about 27 kilometers in a loop under Switzerland and France, is a machine built by humans to recreate the hottest conditions ever known. The cold is instrumental. It is a tool in service of understanding the hot. The International Space Station orbits at an altitude of roughly 400 kilometers above Earth's surface, in the outer fringes of the atmosphere. At that altitude, the environment is not the same as deep interstellar space, but it shares some of its coldest features. In the shadow of the Earth, the temperature of any surface on the ISS drops dramatically. Without sunlight, there is no solar heating, and the only source of warmth is the thermal radiation emitted by the Earth below and the faint cosmic microwave background. Temperatures in the shaded parts of the station and its external equipment can fall to around minus 150 degrees Celsius, roughly 120 Kelvin. On the sunlit side, by contrast, temperatures can rise to over 120 degrees Celsius. The ISS thermal management system is designed to handle this extraordinary swing between extreme cold and extreme heat, using fluid loops, radiators, and insulation to keep the interior of the station at comfortable temperatures for the crew. The cold atom laboratory on board the ISS takes advantage of the microgravity environment to create and study Bose-Einstein condensates at extremely low temperatures. On Earth, an ultra-cold gas cloud is pulled down by gravity, falling out of the trapping region in a fraction of a second. In the microgravity of orbit, the cloud can be prepared and held for much longer, allowing experiments that are impossible on the ground. The ISS, operating in an environment where external temperatures swing by 270 degrees Celsius between shadow and sunlight, also hosts instruments that actively create temperatures billions of times colder than interstellar space. The contrast between the external thermal environment and the experimental temperatures achievable on board illustrates how precisely human technology can control cold in specific, well-engineered contexts, even while surrounded by an environment that is itself extreme. The coldest things in the universe by temperature are objects that humans have built and cooled deliberately. Laboratory samples at picokelvin. The magnets at CERN at 1.9 Kelvin. Cold atom clouds on the ISS. The universe's natural cold floor is far above the temperatures that physics allows and that human technology has reached. But this laboratory cold is temporary and local. It requires continuous energy input to maintain. A Bose-Einstein condensate at picokelvin will warm to room temperature within fractions of a second if the trapping fields are switched off. The cold we create is fragile. The cold the universe tends toward is permanent. The materials that enable some of the coldest technology, the superconductors that operate near absolute zero, have transformed practical technology in ways that are not always visible. The most common superconductors used in current technology are niobium-titanium alloys, which are superconducting below about 10 Kelvin, and niobium-tin, which is superconducting below about 18 Kelvin. These materials are cooled using liquid helium in large-scale installations like MRI machines and particle accelerators. An MRI machine, which is now a routine medical instrument found in hospitals worldwide, operates by maintaining a large electromagnet in a superconducting state using liquid helium cooling. The magnet produces a strong, steady magnetic field, typically 1.5 or 3 Tesla in clinical machines, which aligns the magnetic moments of hydrogen nuclei in the patient's body. Radio frequency pulses then perturb these aligned nuclei, and the signals they emit as they relax back into alignment are detected and processed into images of the patient's internal anatomy. Without superconductivity, without the ability to maintain these strong magnetic fields without resistive losses, MRI would be impractical. The magnets would require constant high-power input to overcome resistance and would generate enormous amounts of waste heat. The technology, which has become indispensable in medical diagnostics, depends directly on the quantum phenomena that emerge at temperatures a few degrees above absolute zero. Quantum computers, being developed by numerous technology companies and research institutions, require their processing elements to be cooled to temperatures in the millikelvin range, tens of thousandths of a degree above absolute zero. At these temperatures, quantum bits can maintain their quantum states long enough to perform calculations. At room temperature, thermal noise disrupts the quantum states almost instantly. The cold is not incidental to quantum computation. It is what makes quantum computation possible. The coldest technology humanity has produced enables some of its most sophisticated capabilities. A memory scanner that reveals the internal structures of a living body. A quantum computer that can explore problems beyond the reach of classical machines. Both depend on cold not as an obstacle, but as an enabling condition for phenomena that do not exist in the warm world. Cold is not just the absence of warmth. It is an enabling condition for the most advanced physics human technology has reached. The discovery of the cosmic microwave background is one of the more extraordinary accidents in the history of science. In 1964, 2 radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large radio antenna to study the emission from the Milky Way. They kept detecting a persistent noise in their measurements, a faint radio hiss that came uniformly from every direction in the sky and would not go away no matter what they did to eliminate it. They checked their equipment. They recalibrated. They even cleaned out the antenna horn because pigeons had been roosting inside it. The noise persisted. It was not interference. It was not equipment error. It was the sky itself, radiating uniformly at microwave wavelengths from every direction simultaneously. At the same time, a group of physicists at Princeton led by Robert Dicke had been theorizing about what relic radiation the Big Bang might have left behind. They predicted that the early universe, hot and glowing, would have produced light that had been stretched by the expansion of space into the microwave range and should still be detectable today. They were building a detector to look for it. When Penzias and Wilson heard about the Princeton group's prediction, and the Princeton group heard about the noise that would not go away, the connection was immediate. What Penzias and Wilson had been trying to eliminate was precisely what the Princeton group had predicted. Penzias and Wilson won the Nobel Prize in Physics in 1978 for its discovery. The story contains a detail worth noting. When Penzias and Wilson cleaned the antenna, they described the pigeon droppings they removed as a white dielectric material. A diplomatic description for what was, in scientific terms, an irrelevant complication. The noise they were detecting had nothing to do with pigeons. It came from the beginning of the universe. The elegance of the discovery lies in this. Penzias and Wilson were not looking for the CMB. They were not theorists who predicted it and then designed an experiment to find it. They were radio engineers trying to study the Milky Way, irritated by a noise they could not eliminate. The most important cosmological discovery of the 20th century arrived as an annoyance, and the noise they could not eliminate was light that had been travelling for 13.8 billion years, carrying the thermal signature of a universe that no longer exists in the form that produced it, arriving uniformly from every direction in the sky, indistinguishable from instrument noise until someone understood what it was. The CMB is not just a temperature measurement. It is the oldest directly observable phenomenon in the universe. It is the boundary of what light can tell us about the past. Before last scattering, the universe was opaque. No light from that era survives to be detected. The CMB is the wall at the edge of the visible universe in time, the oldest photons we will ever detect, carrying the imprint of conditions 1/3 of a million years after the beginning of everything. What the CM contains, beyond its average temperature of 2.725 Kelvin, is information. The tiny variations in temperature across the sky, on the order of 1 part in 100,000, are the imprint of density variations in the early universe. Regions that were very slightly denser emitted slightly different light. Those differences have been preserved across 13.8 billion years, coded into the temperature map of the microwave background. Satellites including COBE, MAP and the Planck Observatory have mapped these temperature variations across the full sky with increasing precision. From those maps, cosmologists have derived the geometry of the universe, the relative proportions of ordinary matter, dark matter and dark energy, the rate of cosmic expansion, and the specific pattern from which all structure grew. The cosmic microwave background is not visible to human eyes. At a temperature of 2.725 Kelvin, the peak of the radiation falls at a wavelength of roughly 9 millimeters, well into the microwave portion of the electromagnetic spectrum, far below the wavelength range that the human eye can detect. You cannot look at the CMB the way you look at a star. You need instruments specifically designed to measure microwaves. There is a connection between cold and information that goes deeper still. In the 19th century, James Clerk Maxwell proposed a thought experiment involving a tiny intelligent creature at a door between 2 chambers of gas. The creature could observe individual gas molecules and selectively open the door to allow fast molecules to pass in one direction and slow molecules in the other. Fast molecules are hot. Slow molecules are cold. By sorting them, the creature would create 1 hot chamber and 1 cold chamber without doing any external work, apparently violating the second law of thermodynamics. The resolution took nearly a century of physics to work out. The creature must store information about the molecules it observes, and eventually it must erase that information to reset for the next observation. Erasing information generates entropy, heat, disorder. The entropy produced by erasing the creature's records exactly compensates for the entropy reduction from its sorting. This is Landauer's principle. Erasing 1 bit of information generates a minimum amount of heat, set by the temperature of the environment. Cold-ordered states cannot be created for free from hot disordered ones. Information processing has a thermodynamic cost. The approach toward absolute zero is the approach toward the maximum order that matter can have, and creating that order requires information, and information has a minimum thermodynamic cost. The coldest widespread glow in the universe is also its most information-dense signal. Cold is not absence. Cold is a record. There is a connection between cold and information that goes deeper still, discovered through a thought experiment proposed by James Clerk Maxwell in the 19th century. Maxwell imagined a tiny intelligent creature standing at a door between two chambers of gas. The creature could observe individual gas molecules and selectively open the door to allow fast molecules to pass in one direction and slow molecules to pass in the other. Fast molecules are hot, slow molecules are cold. By sorting them, the creature would create one hot chamber and one cold chamber without doing any external work, apparently violating the second law of thermodynamics. This thought experiment troubled physicists for decades. The second law says entropy always increases. But the demon seemed to be decreasing it for free. Where was the error? The resolution, which took nearly a century to work out fully, came through the work of Leo Szilard and later Rolf Landauer in 1961. Landauer's principle states that the demon must store information about the molecules it observes, and eventually it must erase that information to reset for the next observation. Erasing information generates entropy, heat, disorder. The entropy produced by erasing the demon's records exactly compensates for the entropy reduction produced by its sorting. This established a fundamental link between the thermodynamics of heat and the thermodynamics of information processing. Every time you erase one bit of information, you must generate a minimum amount of heat set by the temperature of the environment. At room temperature, this is an extraordinarily tiny amount of heat. But it is real, it has been measured, and it is a fundamental limit. The connection to cold, reducing disorder in a physical system, creating cold-ordered states from hot disordered ones, is not just a matter of removing energy. It requires information processing, and information processing has an irreducible thermodynamic cost. You cannot create cold for free. You cannot sort fast molecules from slow molecules without paying a price in information and entropy. The approach toward absolute zero is the approach toward the maximum order that matter can have, and creating that order requires information. The limit is not just thermal, it is informational. The cosmic microwave background is not perfectly uniform. It has tiny variations, and those variations encode the structure of the universe we see around us. In 2004, astronomers detected a region of the CMB in the direction of Eridanus that was measurably colder than the surrounding background, about 70 microkelvins below the CMB average, spanning roughly 1 billion light-years across the sky. This became known as the Eridanus cold spot. The leading explanation involves the Eridanus supervoid, a region where the density of matter is roughly 20% below the cosmic average. Photons of the CMB passing through an underdense region lose a small amount of energy to a gravitational effect called the integrated Sachs-Wolf effect. Passing through the void, the photons emerge slightly cooler than they entered. Whether the supervoid is large enough to fully account for the cold spot is still debated. The cold spot sits at the edge of what standard cosmological models predict, not firmly outside them, but uncomfortable enough that researchers continue studying it. The Boots void adds another dimension. Discovered in 1981, it is one of the largest known voids in the universe. A region roughly 330 million light-years across, containing almost no galaxies. Where the surrounding cosmic web contains the expected density of galaxies, the Boots void contains only a handful where thousands would be expected. The cold of the Boots void is not anomalous in terms of CMB temperature. The background inside is the same 2.725 Kelvin as everywhere else. But the scale of emptiness is the point. To cross the Boots void at the speed of light would take 330 million years. During that entire transit, you would encounter no star, no planet, no gas cloud, warm enough to radiate visible light. Only the microwave background, uniform and cold in every direction for 330 million light-years. The connection to dark matter runs through all of this. The distribution of cold and empty versus warm and dense in the universe is largely determined by dark matter. Dark matter does not interact with light. It is invisible. But it has gravity, and that gravity shaped the cosmic web, pulling ordinary matter into the filaments and nodes we observe. Cold dark matter, the leading model, refers to dark matter particles that were moving slowly relative to the speed of light when the universe was young, allowing them to clump on small scales and seed the fine structure of galaxy clusters and filaments. Warm dark matter, the alternative, would consist of lighter, faster-moving particles. Warm dark matter would smooth out small-scale density variations, producing a different pattern of structure on the smallest scales. The distinction between cold and warm dark matter is not just a description of temperature, it determines the entire architecture of the visible universe. The voids are the spaces left behind. The cold of the universe is not random, it maps onto the matter distribution that dark matter created. Dark matter is the dominant form of matter in the universe. It makes up about 27% of the total energy content, while ordinary matter, the atoms and molecules that make up everything visible, constitutes only about 5%. Dark matter does not interact with electromagnetic radiation. It does not absorb or emit light. It is invisible to every instrument that detects electromagnetic waves. But dark matter has temperature. Its particles were in thermal equilibrium with the rest of the universe in the early hot phase, and as the universe cooled they decoupled from ordinary matter and continued to cool independently. Cold dark matter, the leading model, refers to dark matter particles that became non-relativistic, moving much slower than light, early in the universe's history. Cold dark matter particles are massive and slow-moving, which allows them to clump together gravitationally on small scales and form the halos around which galaxies and galaxy clusters grow. This is why the cosmic web has the structure it has: fine filaments, dense nodes, and vast empty voids. Warm dark matter, the alternative, consists of lighter, faster-moving particles. Warm dark matter would smooth out small-scale density variations, producing a universe with less fine structure on the smallest scales. Some observations of the distribution of small galaxies and the properties of galactic halos may favour some version of warm dark matter or mixed models. The distinction between cold and warm dark matter is therefore not just a description of temperature. It determines the entire architecture of everything visible in the night sky. Cold dark matter produces a universe of fine structure. Warm dark matter would produce a smoother cosmos. The temperature of the invisible dominant component of the universe shaped everything you can see. The Eridanus supervoid is worth returning to with more detail about what its scale means. The supervoid is estimated to span roughly 300 to 1,000 million light-years, depending on how its boundaries are defined. For context, the observable universe is about 93 billion light-years in diameter. The Eridanus supervoid is a significant fraction of the observable universe by volume. Within that volume, the density of matter is roughly 20% below the average cosmic density. This does not mean there are no galaxies at all. It means there are fewer than you would expect, based on the surrounding structure. The cosmic web still exists inside the supervoid. There are still filaments and clusters, just fewer and less dense than in other regions of similar size. If you could somehow travel through the Eridanus supervoid at the speed of light, beginning at one edge and heading toward the other, the transit would take roughly 300 million years. During that time, you would be in a region of space where even the already sparse interstellar medium is somewhat less dense than average. The nearest galaxies would be farther away than average. The nearest stars, already light years apart in ordinary interstellar space, would be even more remote. The temperature of the space around you would be the same 2.725 Kelvin everywhere you went. The cold would not vary noticeably from one point to the next. It would simply be there, uniform, in every direction for 300 million light years. Cold is not dramatic in its presence. It is pervasive in its extent. Most of space is void. Most of the universe's volume is largely empty, filled with nothing but the cooling photon field of the cosmic microwave background. Cold is not an exception in the universe. Cold is the rule. The Boots void is one of the largest known voids, but it is not unique. Voids are a normal feature of the cosmic web. The universe, on its largest scales, is organized into filaments of galaxies connected at dense nodes surrounding vast empty bubbles. The voids are the spaces between the filaments. They are, on average, hundreds of millions of light years across, and they constitute the majority of the universe's volume. Cosmologists estimate that voids make up roughly 80% of the universe's volume. Most of space, by volume, is void. The galaxies, clusters and filaments that contain all the stars, all the planets, and all the life we know of are concentrated in roughly 20% of the universe's volume. The other 80% is largely empty, permeated only by the CMB photon field and whatever dark matter and dark energy fill even the emptiest regions. When you look at a map of the universe's large-scale structure, what strikes most people first is how the galaxies form intricate webs of filaments. But that impression comes from looking at where the matter is. If you could instead look at where the matter is not, you would see that the voids dominate the image. The universe is mostly empty, mostly cold, mostly dark. The webs of galaxies are the decoration on a structure that is overwhelmingly void. This is what cold in the universe actually means at the largest scale. Not a background against which warm things exist. The dominant condition, with warm things as the exception. Cold is not an exception in the universe. Cold is the rule. There is a connection between cold and darkness in space that goes beyond the obvious. As the universe has expanded and cooled over 13.8 billion years, the dominant form of electromagnetic radiation filling space has shifted from visible light to microwaves. In the early universe, the photons were energetic enough to appear as visible and ultraviolet light. The universe was literally bright with its own heat. You could have seen it with your eyes, though there was nothing alive to look. As the universe expanded, those photons were stretched. Their energy decreased. Their wavelengths lengthened. By the time the universe was a few 100,000 years old and atoms could form, the photons had shifted to near-infrared wavelengths. After 8 billion years of stretching, they are now in the microwave range, invisible to any unaided biological sense. The universe was once bright. It is now dark to human eyes for the same reason it is cold. The expansion of space has stretched its radiation from visible to invisible, from warm to cold. When you stand outside on a clear night and look at the darkness between the stars, you are looking through a space that is filled with the microwave background. The darkness is not empty. It is filled with photons, arriving from every direction simultaneously, at a wavelength your eyes cannot detect, carrying a temperature your skin cannot feel. In a very real sense, the universe around you is not dark. It is bright, with microwave light. It is not cold in the sense that there is nothing there. It is warm with the residual glow of the Big Bang. But both the light and the warmth are beyond human perception. Both have been stretched by expansion past the thresholds that biology can sense. The universe is not quiet. It is speaking in frequencies we cannot hear. It is glowing in wavelengths we cannot see. The cold and the dark are not the absence of the universe. They are the universe beyond what we can detect. What does cold actually do to matter? At high temperatures, matter is energetic. Atoms move fast. Bonds form and break rapidly. Chemistry happens at the rates life requires. Chemical reactions need thermal energy to overcome the energy barriers between reactants and products. Living systems, which are collections of chemical reactions orchestrated with extraordinary specificity, require temperatures in a range that allows those reactions to proceed. As temperature falls, chemical reactions slow. Below certain temperatures, specific reactions stop entirely. Enzymes in living cells cease to function when they cool below certain points. This is why hypothermia kills. The chemical machinery of life requires heat to operate, and when heat is removed, the machinery stops. The materials familiar from everyday life mostly freeze or liquefy at temperatures that are warm on the cosmic scale. Nitrogen, which makes up roughly 78% of Earth's atmosphere, freezes at minus 210 degrees Celsius, 63 Kelvin. At that temperature, it becomes a faintly blue liquid before freezing into a white solid. Nitrogen is used in laboratories as a common cryogenic coolant, precisely because its behavior at low temperatures makes it useful for keeping things cold, though not at the extreme temperatures needed for superconductivity. Oxygen, the gas that drives aerobic metabolism, liquefies at minus 183 degrees Celsius and freezes at minus 219 degrees Celsius, about 54 Kelvin. The air you breathe would liquefy and then freeze solid at temperatures that are relatively warm on the Kelvin scale of cosmic cold. Water, the solvent of life, freezes at 273 Kelvin. This is the temperature that defines the 0 point of the Celsius scale, and it is one of the most consequential phase transitions in biology. Liquid water is the medium in which virtually all of Earth's chemistry takes place. Carbon dioxide freezes at minus 78.5 degrees Celsius, 195 Kelvin. Mars's polar caps contain carbon dioxide ice at temperatures cold by Earth standards, but warm compared to the interstellar background. Helium-4 liquefies at 4 Kelvin and never freezes at any pressure. The 0-point vibrations of helium atoms are energetic enough relative to the weak forces between them that the atoms cannot lock into the fixed positions of a solid crystal at any temperature without external pressure forcing them together. This is one of the most direct manifestations of 0-point energy in the physical world. These numbers reveal something about the relationship between cold and chemistry. The materials of life freeze at temperatures that are warm by cosmic standards. The chemistry of life operates in a narrow band of warmth that the universe provides only within a few hundred Kelvin of liquid water's stability range. Below that range, the materials of life are solids, unable to react, unable to flow, unable to do any of the dynamic things that living systems require. Life is, from a certain perspective, a process of maintaining order through energy. Living things take in energy and use it to maintain their own structure, to process information, to reproduce. Cold is the removal of the energy that makes that maintenance possible. Consider what happens to a specific sequence of cooling. Take a drop of water. At 20 degrees Celsius room temperature, The water molecules are moving freely. The water is liquid. Chemistry happens inside it. If you were to place living cells in that drop of water at the right temperature, metabolism would proceed. Things would happen. Cool it to 0 degrees Celsius. The water freezes. The liquid medium of biochemistry becomes a solid. The cells inside, unable to circulate their chemistry, die, not from the cold directly, but from the removal of the medium their chemistry requires. Cool it further, to minus 78.5 degrees Celsius. The carbon dioxide that dissolved in that water when it was a liquid would now be a solid if it were present. The temperatures at which fundamental atmospheric gases change state are passing beneath you. At minus 183 degrees Celsius, oxygen liquefies. The gas that powers aerobic metabolism becomes a pale blue liquid. At minus 196 degrees Celsius, nitrogen liquefies. The most abundant gas in Earth's atmosphere becomes a cryogenic fluid used in laboratory cooling. At minus 219 degrees Celsius, oxygen freezes solid. At minus 210 degrees Celsius, nitrogen does the same. At 4.2 Kelvin, roughly minus 269 degrees Celsius, helium liquefies. And at this point, you are approaching temperatures where the quantum nature of matter begins to take over from the classical thermal behavior. Each of these transitions represents a door closing, a material that was once available for chemistry becoming a solid or a liquid with none of the dynamic properties that chemistry requires. Cold, applied step by step, removes the materials of life from the domain of the reactive and places them in the domain of the frozen. The universe's trend toward cold is therefore over the longest timescales, a trend toward the conditions under which life cannot operate, not all at once, not dramatically, but continuously and ultimately. Cold does not add something, it takes something away. It removes the kinetic energy that allows matter to do anything at all. The fate of cold in the long-term future of the universe follows from physics with a kind of inevitability that is rare in cosmology. Most questions in cosmology involve genuine uncertainty. We do not know the exact nature of dark energy. We do not know whether protons will eventually decay. These are open questions. But the trend of temperature is not uncertain. The universe is expanding. The expansion is accelerating. The cosmic microwave background is cooling. These are observed facts. The conclusion that the universe will continue cooling follows directly from them. In the very early universe, within the first seconds, temperatures were measured in billions of degrees. The universe was a hot, dense plasma in which matter and antimatter were constantly created and annihilated, in which the conditions that modern physics has ever produced were at their most extreme. As the universe expanded, it cooled. Within the first few minutes, it cooled enough for protons and neutrons to fuse into light nuclei. Within a few 100,000 years, it cooled enough for atoms to form and the CMB to be released. Within a few 100 million years, it cooled enough for stars to form. The cooling continues. The stars that warm local regions of space are temporary. They represent matter-burning nuclear fuel stored at the Big Bang. When the fuel is gone, the warmth is gone. The universe returns to the cooling trend that has defined it since the first second. The CMB itself carries this trend forward explicitly. Today it is 2.725 Kelvin. In 13.8 billion years from now, if the universe has doubled in scale, it will be roughly half that. In a trillion years, a factor of roughly 70 times the current age of the universe from now, the CMB will have dropped to a tiny fraction of its current value. The background that currently keeps deep space barely above absolute zero will become a background that keeps deep space even more barely above absolute zero. The asymptotic approach towards zero is not a metaphor. It is a mathematical description of what an accelerating expansion does to radiation temperature over time. The universe expands, the photons stretch, the temperature falls. There is no mechanism in standard cosmology that reverses this trend. Stars are local exceptions to this trend. A star heats a region of space around it by converting nuclear energy into light and heat, but the region is local and the duration is finite. When the fuel runs out, the exception ends, the star cools. The surrounding space, which had been slightly warmer than the CMB due to the star's influence, returns to the background temperature. The warmth we experience in this era is the accumulated exception of billions of stars, all of them burning simultaneously in a galaxy embedded in a cosmos that is slowly, continuously, doing the opposite. The red dwarf stars, the smallest and most fuel efficient, burn for trillions of years. But even they eventually exhaust their hydrogen. When the last red dwarf fades, the universe loses its primary source of heat and light. What remains is a collection of cold objects, white dwarfs slowly radiating their stored heat into an expanding, darkening universe, neutron stars, black holes, and the debris of planetary systems orbiting cold stellar remnants. White dwarfs cool over incomprehensible timescales. They radiate heat into the surrounding space, cooling from the glowing white of a newly formed white dwarf through yellows and oranges and reds, and eventually into cold dark spheres called black dwarfs. Objects no longer visible, no longer warm, simply drifting in the dark at temperatures asymptotically approaching the cosmic microwave background. But the cosmic microwave background is cooling too. As the universe expands, the photons are stretched, their wavelengths grow, their energy decreases, their effective temperature falls. What is 725 Kelvin today will be a fraction of that in a trillion years. The background that currently keeps the universe barely above its floor will itself become a whisper approaching zero. The black holes, which have been very slowly evaporating through Hawking radiation, will eventually dissolve entirely. The rate is extraordinarily slow. A stellar mass black hole would take longer than the current age of the universe many times over to evaporate through this process. But eventually, given enough time, even they release their mass as faint radiation. When the last black hole evaporates, there will be nothing left capable of generating heat. What is left, in the unimaginable depths of the future, is a universe where all structure that could generate heat has finished doing so. A universe where the temperature approaches zero asymptotically, never quite reaching it because quantum mechanics forbids it, but approaching it with no force available to reverse the trend. This is what physicists call heat death, the maximum entropy state of the universe. But it is also, accurately, a cold death, the end of the universe's thermal story. A cold so complete that it stretches across trillions of light years of space and trillions of years of time, approaching a floor that nothing can reach. The warmth we exist in is an anomaly of a young, energetically rich era. The cold on either side of this era, the cold before the first stars formed and the cold after the last stars die, is the universe's default. There is a thought experiment that illustrates what the deep future cold of the universe means. Imagine you could observe the universe across vast timescales, not billions of years, trillions, quadrillions, the first thing that changes in perhaps 1 trillion years is that the last stars die. The stellar nurseries that form new stars exhaust their gas. The existing stars burn through their fuel. The smallest, most fuel-efficient stars, the red dwarfs, last the longest, burning for trillions of years. But even they eventually exhaust their hydrogen. When the last star fades, the universe loses its primary source of heat and light. What remains is a collection of cold objects, white dwarfs slowly radiating their stored heat into space, neutron stars, black holes, and cold planets and moons in the dark. The white dwarfs cool. Over incomprehensible timescales, they cool from glowing objects into cold, dark spheres. Objects no longer radiating significant heat, simply sitting in the darkness at temperatures asymptotically approaching the cosmic microwave background. But the cosmic microwave background itself is cooling too. As the universe expands, its temperature drops. What is 2.725 Kelvin today will be a fraction of that in 1 trillion years, a smaller fraction in 10 trillion. Eventually, the temperature of the black dwarfs and the temperature of the cosmic microwave background will both be approaching zero. The black holes, which have been slowly evaporating through Hawking radiation, will eventually dissolve entirely, releasing their mass as faint radiation. What is left, in the unimaginable depths of the future, is a universe where all structure that could generate heat has finished doing so. A universe where the temperature approaches zero asymptotically, never quite reaching it because quantum mechanics forbids it, but approaching it with no force available to reverse the trend. This is what physicists call heat death, the maximum entropy state of the universe. But it is also, accurately, a cold death, the end of the universe's thermal story. The approach to a cold so complete that it is barely distinguishable from absolute zero. A universe spanning cold that stretches across trillions of light-years of space and trillions of years of time. Step outside tonight and feel the air around you. It has a temperature. The molecules in it are moving, bouncing, colliding, transferring energy with every contact. The warmth you feel on your skin is just the transfer of that kinetic energy to you. Temperature is motion, warmth is movement. And somewhere above you, above the atmosphere, above the few thousand kilometers of thin gas that separates you from the interstellar medium, the temperature drops toward 2.725 Kelvin. The cosmic microwave background fills all of that space, the same in every direction, a 13.8 billion-year-old cooling glow, arriving from everywhere simultaneously, and somewhere, 5,000 light-years from here in the direction of Centaurus, gas is expanding away from a dying star at 164 kilometers per second, cooling to first Kelvin, colder than the background that fills all the rest of space. And in laboratories on this very planet, in rooms you could walk into if you had clearance, matter has been cooled to temperatures that the natural universe cannot produce, approaching absolute 0.1 fraction of a Kelvin at a time, each step harder than the last step impossible. And the universe, across its full extent and its full future, is cooling. Slowly, continuously, without stopping. The cosmic microwave background photons passing through you right now were released 13.8 billion years ago when the universe was 3000 Kelvin and opaque. They have travelled for longer than the Earth has existed, longer than the Sun has burned, longer than any structure on Earth or in the solar system has been standing. They arrive at you travelling at the speed of light, each carrying a tiny amount of energy, each carrying the temperature of the universe, 2725 Kelvin, reduced from 3.00 Kelvin by the expansion of space during the entire history of the cosmos. You are bathed in ancient light right now. It does not warm you noticeably. It does not interact with your body in any way you can feel. But it is there, and somewhere in the deep future, those same photons, or photons just like them, will continue filling a universe that no longer has stars, that no longer has planets, that no longer has life. They will be stretched by then to longer wavelengths, cooler temperatures, arriving in every direction, in every location in the universe, filling a cosmos that has returned entirely to what it was trending towards since the beginning. And even then, approaching zero, they will not have arrived at zero. The photons will still carry some energy. The universe will still have some temperature. The floor will be very close, very visible, very clear, but not yet reached. The word cold appears constantly in descriptions of space, but it conceals a range of phenomena quite different from each other. There is the cold of a planet's night side produced by rotation away from a star. There is the cold of deep interstellar space defined by the cosmic microwave background. There is the cold of exceptional natural structures like the Boomerang Nebula, where physical processes produce temperatures below the CMB floor. There is the cold of the universe's future, the asymptotic approach of the entire cosmos toward absolute zero. And there is the cold of laboratories, where human technology extracts thermal energy from matter far below anything the natural universe produces, revealing quantum phenomena that only appear in this artificial regime. These are not the same cold. They have different causes, different contexts, different physical meanings. What they share is the direction. All of them represent a reduction of thermal energy. All of them represent matter having less energy, moving less, doing less. The direction of cold, regardless of its cause, is always the same, toward absolute zero, the limit that can be approached but never reached. There is something worth saying about the experience of cold that connects the physics to the personal. Cold is the only fundamental physical condition that organisms actively generate heat to fight. Warmth, radiation, pressure, vacuum, all of these are external hazards that organisms defend against through structure and chemistry. But cold is a hazard that requires active metabolic response. Warm-blooded animals, including all mammals and birds, spend a significant fraction of their metabolic energy generating heat to maintain body temperature in cold environments. The metabolic cost of staying warm in cold environments is substantial. An animal in a cold climate must eat more, store more fat, insulate more efficiently, or some combination of all three. The Arctic fox, the polar bear, the emperor penguin, all of them represent evolutionary solutions to the same thermal problem: how to maintain the narrow operating range of warm-blooded biology in an environment that is trying to pull you toward its own temperature. Every warm-blooded animal on Earth is, in a very literal sense, constantly fighting the universe's direction. The universe trends toward cold. Every warm body is a temporary exception. Every heartbeat is powered by chemistry that pushes back against the cooling trend, using energy stored in food, which ultimately came from the sun, which ultimately came from the gravitational energy of the universe's structure at the Big Bang. When you feel warm, you are feeling the universe's anomaly. You are the exception. The cold is the rule. This is not a rhetorical statement. It is a description of the energy inventory of the cosmos. All the stars in the observable universe burning simultaneously contribute only a small fraction of the total energy content of the universe. The The dominant energy component is dark energy, which does not produce heat in the conventional sense. The second largest component is dark matter, which also does not emit radiation. Ordinary matter, the kind that forms stars and planets and people, is a small fraction of the total. Of that small fraction, the vast majority is not in stars. It is in gas and dust and cold objects. The fraction of ordinary matter that is actively radiating heat at any given moment is a small fraction of a small fraction of the total energy content of the universe. The warm, active, radiating part of the universe, the part that contains everything humans have ever seen or touched or studied, is a minor ingredient in a cosmos that is cold, dark, and empty by volume and by energy inventory. Every warm thing you have ever encountered is the exception. The cold is what remains when the exceptions end. There is one more dimension to follow. The coldest things in the universe, by temperature, are objects that humans have built and cooled deliberately. Laboratory samples at picokelvin, the magnets at CERN at 1.9 Kelvin, cold atom clouds on the International Space Station. This creates a strange inversion. The universe, which contains the Boomerang Nebula at first Kelvin, also contains human laboratories that have achieved temperatures billions of times colder than that. The universe's natural cold floor is far above the temperatures that physics allows and that human technology has reached. But this laboratory cold is temporary and local. It requires continuous energy input to maintain. The moment you stop running the refrigerator, the temperature rises toward the surrounding environment. A Bose-Einstein condensate at picokelvin will warm to room temperature within fractions of a second if the trapping fields are switched off. The cold we create is fragile. The cold the universe tends toward is permanent. The word cold appears constantly in descriptions of space, but it conceals a range of phenomena that are quite different from each other. There is the cold of a planet's night side, produced by the rotation away from a star and the radiation of heat into space. This cold can be measured in negative tens to hundreds of degrees Celsius, but is driven by the absence of nearby heat, not by the intrinsic temperature of space itself. There is the cold of deep interstellar space, defined by the cosmic microwave background, 2725 Kelvin. This is the temperature of the photon field that permeates all of space. An object far from any star would eventually equilibrate to this temperature. There is the cold of exceptional natural structures like the Boomerang Nebula, where physical processes produce temperatures below the CMB floor through adiabatic expansion. This cold exists in a defined region and will eventually equilibrate with the surrounding background. There is the cold of the universe's future, the asymptotic approach of the entire cosmos toward absolute zero as expansion stretches the CMB photons to longer wavelengths over trillions of years. And there is the cold of laboratories, where human technology extracts thermal energy from matter far below anything the natural universe produces, reaching temperatures billions of times lower than the Boomerang Nebula, revealing quantum phenomena that only appear in this artificial regime. These are not the same cold. They have different causes, different contexts, different physical meanings. The word cold, used carelessly, can collapse this diversity into a single impression that misses what each type of cold actually is. What they share is the direction. All of them represent a reduction of thermal energy. All of them represent matter having less energy, moving less, doing less. The direction of cold, regardless of its cause, is always the same, toward absolute zero, the limit that can be approached but never reached. The coldest truth about the universe is that even when cold has done everything it can do, even when it has removed every joule of heat it is possible to remove, something remains. A final, irreducible movement, guaranteed by the uncertainty principle, that cannot be taken away. The universe approaches zero. It never arrives. Cold is not the absence of the universe. Cold is what the universe is becoming. Good night.